All right, so in this class, we've talked about position versus time graphs, and we talked about the meaning of velocity, and we talked about how to read the velocity off of a position versus time graph. That's some stuff that's going to be important in the lab today. So just as a reminder, if you have a position versus time graph, and that would look like this. And let's say that this is the position versus time graph, that curve there. And let's say we want to know the sign of the velocity at that instant right there on this graph. Remember that the way you would figure that out is you would draw two nearby points on the graph to the point that you're interested in. You would draw the line that goes through those 2 points and just continue it so you can see it. And then a line that's like that would be a positive velocity. A horizontal tangent line would be a zero velocity. And a line like that would be a negative velocity. So at the point we're looking at, does that red line have a positive, zero, or negative slope?
Negative.
Negative. So at this instant, the object is moving in the negative direction. Okay, that's all just based on representation in math world. That doesn't have anything to do with the actual world of flesh and stickers and funny movies and stuff. So can we tell from this, could we point in the direction of that the object is moving at that instant? Not quite yet. In order to do that, we would have to know first the line that the thing's moving along. You know, maybe it's moving along a line like this. And we would have to know what direction we're calling positive and what direction we're calling negative. So if we said it's moving along this, if we also knew it's moving along this line and the positive direction was this way, which would mean the negative had to be this way. Now we could say, yes, the object is moving in the negative direction because that slope is negative. And that means it's moving this way. Okay? Now we're going to talk about acceleration. And if you remember when I introduced velocity, I said velocity tells you how quickly the position is changing. Just the same way velocity measures how quickly position is changing, acceleration measures how quickly velocity is changing. So acceleration measures how quickly the velocity is changing. Well, if the velocity isn't changing at all, what would you guess the acceleration would be?
Zero.
Zero, yep. And so one thing to keep in mind, this is always helpful. Zero acceleration and constant velocity mean the exact same thing. Okay? They mean, one means the other, and the other means the first one. Okay? Like if you were writing a novel about physics and you wanted to say zero acceleration, but you'd already said that a bunch of times, you could say constant velocity instead, you know? They mean the same thing, they just sound different. So right now we're doing one-dimensional motion along a line. Pretty soon we're going to switch to two-dimensional motion where a thing can move anywhere in a plane. In 1D, non-zero acceleration can only mean that the speed is changing. That's the only way that the velocity can change. And there aren't too many things like this where there's like a really fundamental difference between what happens in 1D and 2D. But in 2D, there's a new thing that doesn't exist in 1D. So in 2D, we'll get to it eventually, a non-zero acceleration can mean two things. It still can mean the speed is changing. But it also can mean that the object is turning. And so we'll see, and as like a kind of a concrete example of that, if you imagine being in a giant parking lot and driving reasonably fast in a circle, imagine going in a circle without changing the speed. Like the whole time you're checking the speedometer and you're going 20 miles an hour the whole time you're going around. Okay, the speed wouldn't be changing, but you know that you'd be having to fight some kind of force that feels like it's kind of pushing you towards the door. You'd have kind of a feeling in your stomach. All of that is the acceleration. And even though the speed wouldn't be changing, the fact that you're turning would mean you would feel that acceleration. Okay, but turning doesn't exist in 1D along a line. There's nowhere to turn. Okay, the units of acceleration. Always have to be units of length divided by units of time squared. And the SI units, therefore, have to be meters per second squared. So at the start of class, I gave you the reminder that on a position versus time graph, the way you read the velocity is you draw the tangent line, and then the slope of that tangent line is the velocity, okay? In acceleration, so on a position versus time graph, acceleration is given by, there's sort of two ways to say the same thing. The concavity, or another way to think of it is the curvature. So for example, a straight line doesn't have any curvature, doesn't have any concavity. But if the part of the graph that you're interested in is part of a curve like that, that's called, well, that's a positive acceleration, and that's called concave up. If the part of the graph that you're interested in is a line and it doesn't matter what its slope is, it could be any of these, you know, that's a zero acceleration. And then if the part of the graph you're interested in is part of a curve like that, that's a negative acceleration, and that's called concave down. And when I was like, whatever, when I had the first class that talked about this, as a young man before the weight of the world had crushed my spirits. Um, I was taught this as concave up is like a cup, concave down is like a frown. And now I'm 51 and that's still how I remember it. So you can remember positive and negative this way. Positive, like think of the attitude of the curve, you know, like that guy has a positive attitude.
Still stuck on the whole way of the world part.
Yeah. Oh, it'll only get worse. And this guy has like a negative attitude, you know. So you can remember it that way. Okay. Any questions about that yet? So let's think of an example. So let's say we have a position versus time graph. And that's what it looks like. And let's think about 3 different points. So first, point A is there. Point B is here. And then I'm going to put C in the middle somewhere. And we want to figure out what are the signs of the velocity and acceleration at points A, B, and C. Okay, so at the point A, to figure out the sign of the velocity, draw a tangent to this curve. Does that have a positive, negative, or 0 slope? Positive, so the velocity is positive. And then I happen to put that at a place where I sort of accidentally squiggled that line, but that's supposed to be like a smooth curve. So at A, is that part of a positive or negative curvature? Negative, yep. So the acceleration is negative at that point. Okay. So velocity and acceleration don't have to be the same sign or anything like that. They're independent of each other in that way. And then at the point B, a tangent line is like this. So is the velocity positive, negative, or 0? Positive. And is the acceleration part of a positive concave up? No. Positive concave down? No. Positive up. Concave up positive curve, or is it part of a concave down negative curve? Yep, so this is a positive acceleration. And now we'll go to C. And so this is sort of a weird one. More than anything, I'm just kind of telling you how this works. But for the slope, it's not too hard to tell. If you draw a tangent line, it would look something like that. So is the velocity positive, negative, or 0? Negative. Yeah, the velocity is negative. And now for the curvature, you can see that, so I'm going to erase these 3 just so we can see it better. Yikes. Okay, forget that one. You can see that it's concave down until you get to about C, and then it's concave up after about C, right? And so at this point where it switches over from one to the other one, the acceleration is 0, okay? You can think of that as, sometimes people call that a saddle point in 2-dimensional graphs. And so the acceleration here is equal to 0 because it's switching at that point from a negative acceleration to a positive acceleration. Okay, let's do a similar example, but notice that in this one, we never even dealt with the real world. All of this is just a mathematical representation. But now we're going to start with a graph. Okay, so there's the graph. And we're going to say that this graph represents an object's motion along a vertical line. And we're going to say the positive direction in the real world is up and the negative direction is down. Okay? And so now what we want to know is draw arrows in the direction of the velocity and acceleration in the real world. Okay, this is a picture of the real world over here, and that line shows the line along which the object is moving in the real world. And the instant we're thinking about, let's just choose this as a representative instant. Okay, let's do velocity first. So a tangent line at this point looks something like that. Is the slope of that tangent line positive, 0, or negative? Negative. And so the velocity now in the real world is going in the negative direction. Okay? The negative direction is down. And so the velocity is this way. Okay? Are you with me on that? And now the acceleration. Is that part of a concave up or concave down curve? That's concave down. So the acceleration is negative. And so the velocity of the acceleration is in the negative direction. Okay? So that's the connection between the mathematical representation and what's really happening.
Wouldn't it be like accelerating at that point though?
Okay, so I think that sort of relates to the next thing I'm going to talk about, because I think it's very natural. I think it's sort of connected to the way we talk about acceleration. We talk about if something's speeding up, it's acceleration. If it's slowing down, it's deceleration. So it's pretty natural to think a negative acceleration would be slowing down. And then it gets a little confusing because if you look at the slopes, this is actually getting faster here, but I said it as a negative acceleration. So, okay, here's the thing. Negative acceleration does not mean slowing down. Positive acceleration doesn't mean slowing down. To figure out whether something's speeding up or slowing down, you have to know the signs of both the velocity and the acceleration. So this is sort of like a key thing to remember about the meaning of acceleration. If the velocity and acceleration have the same sign, then the object is speeding up. if the velocity and acceleration have opposite signs, then the object is slowing down. And then I'm going to give you one more. This is kind of, I put this in parentheses. If the velocity is 0, okay, and the acceleration isn't 0, then is the object speeding up or slowing down? Well, to make sense out of that, you have to think, what does velocity equals 0 mean? That means the object is just sitting there, it's not moving. And so if an object is just sitting there and it's accelerating, then it has to be speeding up. You can't get any slower than sitting there, okay? So let's look back, yes?
So then velocity is 0, but acceleration is not 0. Would the object be turning or like?
Okay, so good question. That means that it's a little hard to visualize this stuff. You have to kind of think of time as being broken up into infinitesimal intervals. But what it means is the object, and really, I guess you could make sense out of it by looking at the position versus time graph. Let's see if that helps. I'm going to try to draw it like that. Okay, so let's say the position versus time graph looks like this. Okay? And let's think about the motion at this instant here. Okay? A tangent line is horizontal, so the velocity is 0. But you can see clearly it never stops being concave up. So it is accelerating, even though it's stopped. And it's not turning or anything. It's just like, how do you describe it in like everyday language? I mean, it's basically like it's starting to move, but you haven't given it enough time to really be moving yet. Yeah. Any other questions right now? Okay, well, let's look back at a couple of the examples I've drawn above and think about whether the objects are speeding up or slowing down. Okay, so let's start with this one. At that point A, is the object speeding up or slowing down? You can see, well, I have all the answers here below. The velocity is positive. The acceleration is negative. So which one is it there? Slowing down. And it makes sense if you think like, okay, here the velocity is whatever that slope is, a relatively big number, okay? Here, a little bit later, it's at rest. That's a 0 slope. So if the thing's going from a high speed to rest, it has to be slowing down, okay?
It's just not like stopping randomly.
Right. It's nothing that we look at is going to be happening instantaneously. Everything's going to happen over time. And that's how it is in real life too. Things can stop abruptly, but if you look at it in enough detail, you'll see that it's just slowing down really quickly, you know. Okay, how about at B? That has a positive velocity and a positive acceleration. So that's speeding up. And you can make sense out of that because at this point, the tangent line is horizontal. So it's stopped. And then a little bit later, it's moving. So it has to be speeding up. The one at C, since the acceleration is 0, it's not changing speed at all, just at that instant. Okay. Okay, so now finally we're going to get into some calculations, be able to do some calculations. We are going to be only doing calculations for constant accelerations right now. So these are the constant acceleration equations in 1D. What does constant acceleration mean?
Always accelerating.
It doesn't mean that actually, because you could have a constant acceleration of 0. It just means that whatever the acceleration is at one instant, it stays that way forever for the whole problem. Okay, so let's look at some of these and see which ones might be constant acceleration and which ones are definitely not constant acceleration. Okay, so in this example, notice that the acceleration was negative, and then at B it's positive, and in between them it's 0. So could that be constant acceleration? It can't. So we would never see a position versus time graph like this for our constant acceleration calculations. Okay, what about the next one? Is it possible that this is constant acceleration? Yeah, it's concave down the whole time. We don't know what value it is. We'd have to do the math to figure that out. But at least from what we see, sure, it's possible that that's constant acceleration. So not every motion has constant acceleration. And the most notable case that we'll deal with in this class that's not constant acceleration is circular motion. An object that's moving in a circle does not have constant acceleration no matter what. But we're going to do calculations for constant acceleration because some really important motions do have constant acceleration. Okay. So let me say, but some important ones do. And the most notable constant acceleration motion, let me say, most notably projectile motion and free fall as long as the air resistance isn't too significant. So as long as you can ignore air resistance, is constant acceleration. Okay, so I'm going to basically kind of lay out some theory that is going to be kind of dry and it won't make a ton of sense yet. And then I'm going to go back and do a bunch of examples and show how it works. And then that's when it'll start to make sense. So I'm going to start by saying we're just defining some variables. Let P sub I and V sub I, so that's the initial position and the initial velocity. Let these be the position and the velocity at time equals 0. So this is the position and the velocity when you click the stopwatch on. And then let P sub F and V sub F, so that's like position final and velocity final, be the position and the velocity at time t final. Okay, so this first one is when you click the stopwatch on. The second one is when you click the stopwatch off. And now someone's thinking like, well, actually that other button for the stopwatch is to reset it, but let's pretend that this is how they build stopwatches. Then here are the three constant acceleration equations. The first one says V final is equal to V initial plus A times T final. Notice that A doesn't have initial and final, and that's because A is constant, so it stays the same over the whole calculation. Okay, there's no difference between what the acceleration is when you turn the stopwatch on and off. The second equation says P final is equal to P initial plus V initial times T final plus 1/2 times A times T final squared. And the last one says 2 times A times the quantity P final minus P initial is equal to V final squared minus V initial squared. So those are the three constant acceleration equations. Have you ever heard the expression distance equals rate times time? That is actually a sub-case of this second one. So distance equals rate times time only works if the acceleration is 0. Okay, so it only works like, it works if you're driving your car and you're going basically 60 miles an hour the whole time, right? Because there's no acceleration. In that case, this is gone. The third, fourth term, whatever. You can subtract this over, and so P final minus P initial is like a total distance. And so then it says the total distance is equal to the velocity times the time. Okay, but notice that distance equals rate times time does not work in a more complicated case where you're accelerating. So just, I sometimes see that on people's homework, distance equals rate times time. And it's true in some cases, it works perfectly well in some cases, but notice that it's contained in this equation. So just use these three equations. You never have to go out and use a different equation than those, okay? And now I'm just gonna give you a set of 4 general steps for using these. And then we'll just go through a bunch of example problems. Okay, so the first step for using these equations is in the real world, choose a position equals 0 location. Like imagine putting a sticker down at this spot in the world that you're going to call 0. And choose a positive direction. Okay, imagine having like an arrow sticker that you put down. And once you choose the positive direction, you've automatically chosen the negative direction. It's just the opposite way. And then you need to choose two more things. Choose an instant that you're going to call time equals 0. That's when you turn the stopwatch on. And choose an instant time final where you turn the stopwatch off to look at the value. Okay. You're always going to choose these based on instance. When you know or want information. Okay, like if you're timing a 100-meter dash, you wouldn't turn it on when the race starts and then turn it off at a random time an hour after the race ends. That's because you're not interested in information an hour after the race ends. You want to see what happens at this significant instant when the race ends. Okay, second step. List out the variables that you know and want out of this list. So out of a list of, there are 6 total variables that show up in these equations. And those are time final, acceleration, P initial, P final, V initial, and V final. And we're going to list the variables we know and the one single variable that we want to calculate. Third, if you're lucky, this is the last step. Not always, but often it is. Look for a constant acceleration equation out of those 3 I gave you. And in order for an equation to work, to solve what you're looking for, it has to have the variable you want. And every other variable in the equation has to be known. And that's kind of a wordy way to say it. It's hard to come up with a good, clear wording for that. But all that's saying is, what do you need in order to use an equation to solve for a variable? You need to have one thing in the equation be the variable you want, and everything else just has to be numbers, you know? And then step 4, I'm going to put this in parentheses because you're kind of hoping going into it that you're not going to need to do this. But if no equation works, use an equation to solve for either time final or acceleration, and then go back to step 2. Okay, so say there's a case where you're trying to calculate the final velocity, and you look through the equations, none of them give you what you want, then look for an equation that'll let you solve for either time final or acceleration. Those are the 2 that are most often helpful. that'll let you solve for one of those. Now you know one more thing. Now go back to step 2, list out what you know and want, and see if it works now. Okay. Okay, so for the first example, let's say that a car is traveling 40 meters per second. And hits the brakes. Oh, computer crash. And then the car slows down until it stops 60 meters away. First, we want to know what's the acceleration. And then second, how long in time does it take for the car to stop? Okay, I'm going to start by drawing out just a little kind of diagram of what this motion looks like. So let's say that the car is moving from the left to the right. This is where it hits the brakes on the left, and this is where it comes to a stop on the right, and so those two are 60 meters apart. Okay. At that instant on the left, it's moving with a velocity of 40 meters per second. And at that point on the right, its velocity is 0 meters per second. And that's all we know for now. So now we're going to get into the steps of how to use these equations. Anybody have any questions about this yet? Okay. Okay, so I'm going to start with part A, and I'm going to think of these as 2 totally separate questions. So first we have to choose where to put our stickers, what our 0 position is, what our positive direction is, and then we have to choose when to turn the stopwatch on and off. Okay, it's kind of an interesting fact that you have to make all 4 of these choices, but it doesn't matter to the problem what you choose for your position equals 0 in your positive direction. No matter where you put your stickers, you can get the right answers on these questions. The numbers you get out will look a little different, but once you kind of analyze it, you'll get the same answers. But if you don't start and stop your stopwatch at the right time, usually there's no recovering from that. So you gotta be careful with those. I think most people would probably choose the 0 position to be where the start of this motion is, and the positive direction to be in the direction that the car is traveling. Okay, so let's do that, but we could make other choices. That means the negative direction is to the left. And now that we've chosen these, we can come up with a position label for when the car comes to rest. If you start at 0 and go 60 meters in the positive direction, what's the position here? Yeah, positive 60 meters. So I already showed my position and direction choices in red. When are we going to turn the stopwatch on? Yeah, when you hit the brakes, the start of that motion. So this is going to be the instant you hit the brakes. And what's going to be the instant when we turn the stopwatch off to look at it? Yeah, when you reach zero velocity or when you reach rest. And now we can go through this list of variables and list out which ones we know and which one we're trying to find. Do we know what the stopwatch says when we hit stop? No, we don't. That's the question for part B. For now, we don't know it and we don't care about it because that's later. We'll worry about that when we get to it. So I'm just going to cross that off. It doesn't go anywhere. Do we know the acceleration? No. Do we want it? Yeah, that's the thing we're trying to find on this one. So I'll put it over there. Do we know, so the initial position, remember that's the position when the stopwatch goes on. Do we know that? Yes, we do. That's where we chose to be our zero position. So PI is equal to 0 meters. Do we know the car's position when we turn the stopwatch off? Yes. So P final is equal to positive 60 meters. Do we know the velocity of the car at the instant we turn the stopwatch on? Yes. Okay, so this I want to say a little thing about. So what we're given in the question is a speed, right? It's traveling 40 meters per second. In order to make that a velocity, we have to combine that with the direction that it's moving. So now we have to look at this diagram and say, okay, this thing is moving to the right. Is that our positive or negative direction? Yeah, that's what we chose as positive. So I'm just always, you don't have to do this, but I like to just always be clear to myself that yes, I've thought about the direction of this, you know. So I'm going to call this positive 40 meters per second. And then the last one is when we turn the stopwatch off, do we know the velocity? Yes, rest always means 0 velocity. So V final is equal to 0. And now we're going to go through those equations and see if there are any that'll let us solve this. Okay, so I'm just going to go through them and we'll just check to see if they work. So let's try the first one first. V final is equal to V initial plus A T final. Okay, so the first question is, the equation doesn't do us any good if it doesn't have the thing we're looking for. Well, this one does have A, so that's a good start. Okay, now we're going to go through the rest of the variables in the equation and make sure we know everything else. So V final, do we know it? Yeah. V initial? Yep. What about T final? No. So we can't use that because that's two unknowns in a single equation. So you can't solve for either of them. Okay, you can only find one variable with one equation. So now we'll go on to the second one. And right there you see the problem again. It has TF in it, which was the problem last time, right? So this one isn't going to work either. So it all comes down to the third equation. So 2 times A times the quantity PF minus PI is equal to VF squared minus VI squared. Okay, does it have A in it? Yes. And now we'll go through the rest of the variables. Do we know PF? Do we know PI? Do we know VF? Do we know VI? So this one should work. And now I'm just going to plug stuff in and hopefully we can do the algebra and solve for A. One thing, I used to make people put all the units in as you went through. I just wanted to say that so you know that I'm nicer now. But if you put the units in for every variable and cancel out any units as you go and then divide the units and you're really careful with all that, the answer you get is going to show the proper units. It's really cool how it works actually. And so in a way that's sort of a nice thing to do because you can check, that's a way you can find mistakes you might have made if the units don't come out right. But it takes so much time and effort and stuff. I'd say I'm just gonna put these in as numbers, and at the end I'm just gonna assume the units came out right, and I'm just gonna put down the units for that variable that we solved for. Okay. So 2A times the quantity. P final was 60. PI was 0. And that's equal to 0 squared minus 40 squared. Be sure you notice that that negative is outside of the square. That's remember PEMDAS? Did you learn that in school? So the exponent is applied before that negative sign. So we got 40 squared. And so this gives 120A is equal to negative 1600. And so A is equal to negative 13.3 repeating meters per second squared. Any questions about that? I think this is a good idea to do a sanity check at the end to make sure that if you calculated a velocity or an acceleration, make sure that the signs correspond to what you expect to happen. So like in this problem, we know that the car is slowing down, right? So we know the velocity and acceleration have to have opposite signs for it to be slowing down. Well, the velocity over this whole motion is positive. It goes from positive 40 to 0. So we expect the acceleration to be negative. So that's a good sign. Okay, so now we're on to part B. So the first step is to make your choices of 0 position, positive direction, time equals 0, and time final. In maybe most problems, a lot of problems at least, you can keep all the same 4 choices from the previous part. And anytime you can do that, you want to do it because then you can use all the variables you had before. Okay. If we changed those, we'd have to refigure out what all those variables are. The only time that you have to make a change is if the second part of the question asks for something at a different instant than at one of those 2 instants that you've already named. So like, if I asked, how fast is the car going when it's traveled 30 meters? Now our old stopwatch times instants don't work anymore, and there's nothing we can do. We have to choose a new instant. But this one, our old instants work fine. And so we're going to keep the same 4 choices. And so that means when we go to figuring out what we know and what we want, I mean, I'm not even going to write that out. I'm just going to so we have the column of stuff we know, and the column of the thing that we want. And what we know now is all the stuff we knew before, plus now we know the acceleration. So I'll just list them out again. Initial position is equal to 0. Final position is equal to 60 meters. Initial velocity is positive 40 meters per second. Final velocity is 0 meters per second. And the acceleration is negative 13.3 repeating meters per second squared. And the thing we're trying to find is time final. Okay, so now we're going to go through those same three equations, see which ones let us calculate this. So I'll start with this one. Does this equation have TF? Yes, that's good. Do we know V final? Do we know V initial? Do we know acceleration? Yeah, so this one already works. I think the position final equation, the second equation, would also work here. But anytime you have the chance to use this one, it has the fewest variables in it. It doesn't have any squares, so you don't have to worry about taking square roots, and then you have a plus minus thing going on. So always use this if you can. So 0 is equal to 40 plus negative 13.3 repeating times time final. And so 13.3 repeating times time final is equal to 40. And so time final is equal to 3.0 seconds. Any questions about that? Okay, let me do another example. Let's say we have a ball rolling down a ramp. And the higher point on the ramp is A, and the lower point on the ramp is B. And the ball is just going down this way. At the point A, we're given that the speed of the ball is 2 meters per second. And at the point B, so if a ball is rolling down a ramp, would it be faster or slower, lower in the ramp? Faster, yep. I mean, unless there's a lot of friction for some reason. But, so I'm going to say that this is 5 meters per second when it gets to B. And let's say that we're given that the elapsed time between those two instants is 1.0 seconds. And we want to know what's the distance between the points A and B. So the first thing we have to do is make those 4 choices. Let's make this our 0 and make this our positive direction. And, okay. And now we have to choose when to turn the stopwatch on and off. So when are we going to turn the stopwatch on? Yep, so that's when it passes A. And when are we going to turn it off? So when it passes B. And now I'll list out the 6 variables and we'll figure out what variables we know and want. Okay, do we know when we turn the stopwatch off what it says?
Yes.
We do, in this case. Yep, it says 1 second. So time final is 1 second. Do we know the acceleration? We don't, but if we can solve this problem without it, we're happy, so I'm going to leave it off. Do we know the position when we turn the stopwatch on? Yep. So PI is 0. Do we know the position when we turn the stopwatch off? No, but that's what we're looking for, right? If we could figure out that position, we can figure out the distance between those two. So this is what we want. Do we know the velocity when we turn the stopwatch on? Yep. And the speed is 2, so you always just need to mental check whether it's moving in the positive or negative direction. In this case, it's positive. So I'll write this as positive 2. And do we know the velocity when we turn the stopwatch off? And that's positive 5 meters per second. Okay, do any of the 3 equations work for this? Well, the problem here is we need the equation to have PF. That's what we need to solve for, right? But we don't know the acceleration, and notice that all 3 of these equations have acceleration in them. And so we can't do it. No equation works. And it's okay to take a second to just feel sad. That's supposed to be like a puddle of tears. Okay. But then after, give yourself time to get over it. But then the next step is we want to find an equation. Well, it's pretty obvious what equation we want to find here. I mean, it's almost always going to be either time final or acceleration, and we already know time final. So we're going to try to find acceleration. Okay, so now it's like you can say, okay, we're going to set this aside for a second, and we're going to see if we can find the acceleration. So again, let's just go through the equations and see which ones work. So this one has A in it. V final is known, V initial is known, and time final is known. So this equation is going to work for us to calculate A, not to solve the problem. So we have 5 is equal to 2 plus A times 1. Okay, and now you're just doing the algebra. So 3 is equal to A. So A is equal to 3 meters per second squared. And do the sanity check on the signs. Is this ball speeding up or slowing down?
Speeding up.
Speeding up. So do we expect velocity and acceleration to have the same sign or opposite signs? Same. And so our velocities are positive, our acceleration is positive, so that all makes sense. And now we'll go back. Now we know this. So like basically you can take this include that in the column of stuff that you know, and now look back through the equations, and we should have some options now. So V final is equal to V, well, we know that's not going to work because we already solved for the one variable we didn't know. What about this one? P final is equal to P initial plus VI time final plus 1/2 A time final squared. Okay, we're trying to find P final. That's in this equation, so that's a good sign. That's a good start. Do we know P initial? Yes. Do we know V initial? Yes. Do we know T final? Do we know acceleration?
Yes.
Now we do. We just solved for it. So this will do it for us. So P final is equal to 0 plus 2 times 1 plus 1/2 times 3 times 1 squared. And so P final is equal to 2 plus 1.5, so 3.5 meters. So the points A and B are 3.5 meters apart. Anybody have any questions about that? Okay, I'll stop there. And next time we'll talk about free fall and projectile motion. And I'll give you some problems to work on before Wednesday.